All right, guys. So let's do this. Which one? Where did we stop last time? Hey, Therese, can you go back to the picture to see if I'll centralize you? That's good. All right, thanks. All right. So we related work to Newton's the first law to conservation of energy. So if you do no work, there cannot be a change in the amount of mechanical energy in the system. So formulas again. All right, formulas again. I'm gonna try to finish this today if I can. So that next class we can do practice. But what is the formula for kinetic energy, Chris? Do you know? Yeah.
Is it half?
Yes. What about gravitational potential?
Oh, that's mgh, right?
Yes. What about spring potential? Right. What about change in kinetic energy? Is just that thing right there? Or like this, you have to put final squared minus initial squared, right? And then change in potential energy, let's talk about gravitational potential. It's just mg h final minus h initial. At the end of last class, I talked about how change means more than absolute, right? Because the absolute depends on the reference point, correct? But the change is always the same no matter which reference point you take. That's why we worry more about change. Now, I also talked about the fact that you can think of work as, right, force times distance, as in like a dot product between two vectors, which is actually doing this, F, D, cosine of theta, all right? But when you do work, basically when you apply a force over a distance, you do work. Let's talk about some applications of this before we start, okay? This is very important, guys. I don't know if it's going to show up later or not, but this is important stuff, so make sure you understand. So I'm holding this. Am I doing work? Why not? No displacement. So you look at the formula and you think about why or why not. Always look at the formula, okay, before we do this. So now I am holding this, right? And then I'm carrying the book across the room like that, right? Am I doing work against gravity? Why not? No displacement this way. Are you with me? Now, I pick up the book from the floor. Did I do work? Right, why? But doesn't it depend on whether or not, okay, no, it's another thing. When you do work, or when something does work on the system, two things have to happen. Either you change kinetic energy, or you change potential energy. All right? Or you can think of it as this way, that if you lose potential, you gain kinetic. Right? So these are things that govern this chapter. Now pay attention to this. What if I raise this at a constant rate? Is that change? It might change the kinetic energy of it. So it's moving at a constant velocity, and I keep it going at a constant velocity out. Is the kinetic energy changing? No. So if I look at it that way, how much work did I do? Right? So the better way to think about it is actually this. That is the work energy theorem, is what it's called. Are you with me? Now, if work is zero, then that means that change in kinetic energy must be equal to change in potential energy. Does that make sense? Now look at it. If you put zero here, you send delta to the other side, you get that. Are you with me? When work is zero, you get that. Right? So that is the most important thing here in this chapter. So let's think about that. I'm not changing kinetic energy because I'm going across velocity. So if I'm going across velocity, this number will be the same, which makes this zero, which makes that zero, so that's zero. But does that mean I do no work? No, because there's something else. Which is what? The changing potential. Am I changing the potential when I raise the book up? So do I do work? Yes. Does that make sense? All right. So how about when this falls? Now it's interesting. It depends on how you think about it. Was there before it hit? Was there a change in potential? What was that doing to it? What was happening to it? It was decreasing. You can think of it that way, right? Or you can think of it as, is the change in kinetic energy happening? Yes. So you can think of that. The loss in potential energy resulting in increase of this. Because when this number becomes negative, that becomes positive. Does that make sense? When this is a loss of potential, this is a negative number, the delta U. Because the final height is below the initial height. That means this number is bigger than that number. You get a negative number over here. If that number is negative, within the negative side over here, that means that's positive. But even if that's positive, that means you gain velocity. Right? Does this follow? Okay. So if you gain velocity, that's one way of thinking about it. But there's another way you can think about it. You think about it, instead of you have lost potential, you can also think of it in terms of gravity did work. See? Forget the potential change. And just think about what the work that gravity did must be equal to change in kinetic energy. Now check it out. What is work? Force times distance. Does that make sense? What is the force of gravity? What is that called? Your force of gravity. Weight. What is the formula for weight? Mass times gravity, right? And the distance that it's falling the height, isn't it? Alright, so that's mgh. Isn't that the same thing as gravitational potential? So you can think of gravitational potential as the stored work that gravity can do. Does that make sense? Right? So, but be careful. Don't think of both at the same time. Either you think of it as work done by gravity, or you think of it as a gravitational potential loss. Right? Otherwise the formula doesn't make sense. You're going to put work here and here. You put the same numbers on both sides, and then it doesn't make sense. Alright? But you can think of it either way. Another situation about doing work or not doing work. Right? So, two linemen on football. Right? So the snap happens. You know what happens as soon as the snap happens? The offensive linemen, what do they want to do? No, the offensive linemen are not attacking. What are they doing? It's ironic, but the offensive linemen are actually blocking the defense from attacking the quarterback, right? What are the defensive linemen doing? They're trying to rush the quarterback, or at least block the pass or something, all right? So they're trying, and that happens in any football game. It's like a little war of force, right? They're pushing against each other. Of course, if one pushes harder than the other, then the guy goes backwards. And that always happens, But my question is, imagine two guys pushing against each other as hard as they can, neither of them is moving. And they're getting tired. Those muscles are, they're grunting and they're getting tired. How much work are they doing? Why not? There's no displacement. You get this, and you lift it up, and then it falls. And you lift it up, and it falls. And then you lift it up, and it falls. How much work was done on the book? Why not? Now, here's where it's tricky. You gotta be very careful. This is how it's gonna get you on the test, so pay attention. Be very careful the way the question is asked. Because I said how much work was done on the book. What if I the same situation, but I changed the question? How much work did gravity do? Did gravity do work on this situation? Lots of work, right? To pull it down every time. And actually, it did 3 times this thing, right? If I said how much work did I do work? Yeah, but all the work I did, gravity undid. So no work was done on it. Does that make sense? Which is why at the end, it had the same potential and the same kinetic energy as it started with. Does that make sense? Does that make sense? Because they're canceling each other out. So, but that doesn't mean that I didn't do work. It does say, I can do work, gravity can do work, but no work was done on it. So you think of that as that, if there is no net force, then there is no net work. Because, so another way of thinking about it, no net displacement or no net force. Either way, there's no net work. Does that make sense? Here's another example. So I push this book on a surface, right? Now it's on the table, right? And I'm pushing the book on the table, right? At a constant velocity. Am I doing work? Let me ask, Dave, am I doing work? This is what's tricky for people to understand. It's moving at a constant velocity. Does that mean there's a force acting on it or not? No force acting on it? There could be force acting on it. Or there could not be force acting on it. It's moving at a constant velocity. So according to dynamics, just finished covering it's moving at constant velocity. Does that mean there's an acceleration? No acceleration, no force. F equals ma. So if A is 0, force is 0. Does that make sense? So there's no force. If there's no force, how could you have work? So is there work on this object? No, but that's not what I ask, is it? I ask if I'm doing work. Well, let's think about that. Am I applying a force on this thing? Over a distance. So am I doing work? Okay, so why is the object not accelerating? Now, if I'm applying a constant force over a distance, yes? It's not about not enough force. Think about it. If I have a force applied, and that's not causing acceleration, what's the problem? Yes? Another force must be acting on it just as much. What's the force? Friction. So if I'm pushing, and friction is pushing exactly the same backwards, it's going to move at a constant velocity. No work is done on the object, but friction did work and I did work. Do you distinct? This is a very important distinction. You can do work, friction can do work, and yet no work was done on it. Does that make sense? So in what circumstance does work actually done on it if the work you do is bigger than the work of friction? Does that make sense? Now let's talk about work done by friction. Can work done by friction accelerate an object? Because people have that misconception. Now when I slide, I can even slide with these shoes. They're high grip shoes for rock climbing, right? I can't slide. But before in the class, you saw me doing it a few times, right? When you slide. When you slide and it stops you, what's stopping you? Is that work that's acting to accelerate you or decelerate you? Decelerate you. Can friction do the opposite? Speed you up. Right. Every time I take a step, right? Static friction can do that. Exactly. Very good. Because when I take a step, what's pushing me forward, really? I'm pushing the ground, and the ground pushes me forward. That's friction. The car moving, that's friction. So can friction do positive work? Absolutely. Is that the same? Which brings me to the actual next question. And now I can go through it because we actually talked about a lot of things. Hopefully we'll be able to go through it a little quicker than we would if otherwise. The next question is, what is the sign of, okay, which of the following can be negative? Did we do them already? Did we do number 3 already or not? No. Which of the following can be negative? If so, explain the meaning of that negative sign. Okay? So, you guys are going to help me out now. Alright, so in this, can kinetic energy be negative? Look at the following before you answer. Is there a way for this to be negative? How? Sure, but that's not kinetic energy. That's change in kinetic energy. So I did that on purpose to make people not get confused in the test. Don't look at this formula because that's not kinetic energy. That's change in kinetic energy. Does it make sense for change to be negative? Of course, you're slowing down. That's kinetic energy. Can that be negative? Only if you had negative mass, right? This is squaring. But negative is a scalar, right? Is there a constant of negative mass? Some people think there is. But right now, we don't, right? Okay, let's not go there. Not now. Okay, but there's actually this is actually at the forefront of physics right now. A lot of people think that there might be something called negative mass that we haven't detected in the universe. And the negative mass exerts negative gravity. So what does gravity do to things? It pulls them closer, right? So what would negative gravity do? Expand things, and that would expand dark energy, which would expand the universe and things go faster and faster. So there's some people that actually think there might be some sort of thing called negative mass that we can't detect out there. And there must be more of it than positive mass because the universe is not contracting but expanding faster and faster.
Well, my eyes don't want
No, I think that's different. But maybe it's the same. Maybe mass is not an absolute natural value. Maybe it's actually interesting. But going back to what we actually have to say. Can kinetic energy be negative, therefore? No. Because it's hard for me to even conceptualize. What does that mean? Negative kinetic energy. What is it doing? Because 0 means it's not moving. Positive values means it's moving. So what does negative mean? Are you with me? It doesn't make sense. Okay, so let's talk about the next one. Potential energy. What is this? 1. Can potential energy be negative? Look at the formula before you answer. What's the formula for potential energy? Okay, so can M be negative? No, G is already a 9.8 value. Don't put a negative on G. We talked about this at the beginning of the year. If it says A, you're plugging in gravity, you're plugging in negative 9.8. But if it says G, you're just plugging 9.8. So that's also not a negative number, right? Can H be negative? Can height be negative? Of course. It depends on where you put the 0. Does that make sense? So can potential be negative? What does that mean, though? What is the meaning of negative potential? So let's think about that. Lautaro. Hi, what does it mean to be negative potential? No, remember, not necessarily. I could be going up, but I'd be below the 0. So what does negative potential actually mean? Negative height. It just means that I'm below where the 0 was registered. Does that make sense to you? Did you finish both things? So now you're... Okay. Alright. What did I say? Right, exactly. So if you have negative height. But negative height is just a constant that means like I set the 0 here because I chose the 0 to be here. Yes. Yeah. Yeah, because someone else is going to test. Alright? Remember, you don't have to do that question. You don't think you're going to go to the next one. Do as much as you can, okay? Yes. It depends. Not really. Okay. That's a great question, too. Give her Legos. Alright? By the way, if you participate, ask questions, make comments, make sure you get your Legos, okay? Now, what I'm saying here is negative. Okay, so she made a very good question. If you have negative potential, does that mean you have potential to go to 0? Well, let's think about what that means with gravity. If I'm at positive potential, what is the natural tendency for me to do if I let go? Go to 0 and gain kinetic because of that, correct? Unless it's a force holding me there. Does that make sense? But if I have negative potential, where am I? I'm below wherever a 0 was established. Am I going to naturally go up to 0, or do I have to go to more negative, even more and more negative? More? Are you with me? Potential tends to drop unless a force has to raise it or hold it there. Does that make sense? Yes? Now, 0 just means it's below what you set the 0 is going to be. So if I say how much potential does my hand have right now, talking about this last class, that actually has no meaning because in itself, because I can call this the 0, and that means there's no potential. Right? But if I call that 0, then it has a little bit. If I call that 0, it has a little bit. If I call that 0, it has negative potential. Right? So what is the only way you go from negative potential to 0? Something has to raise you up. So are you with me? So you have to lose some kinetic energy, or some work has to be done. That's the only way to gain potential. Lose kinetic, or work was done. Does that make sense? All right. What about negative work? Look at the formula and tell me if it's possible. FD cosine of theta. Can you have negative work? How? Can displacement be negative? Yes. What does that mean? Yeah, that went left, right? Or can force be negative? Absolutely. What does that mean? It's a force that's doing what? It's against the direction of work. Sure. So, how could you do negative work then? Yes. Right? So very good. So, now, what does negative work do to, say, kinetic energy? What does the negative work do to kinetic energy? If you're going fast and you do negative work, what's going to happen? It's going to decrease. So what does that negative work do? Slow things? No. Or what does it do to potential? Negative work. No. You have to look at the formula. If you do negative work, what has to happen to either potential or kinetic? So see that's what gravity does. Gravity does, in the sense of losing potential, negative work. Right? But in the sense of gaining kinetic, because it's going down faster, it does positive work. But anyways, let's talk about the next. So anyways, this is important. Positive work means gaining kinetic energy. Negative work means losing kinetic energy. Does that make sense? Guys, make sure you're writing stuff down, right? You have to answer them. All right, let's go. 4. What is the sign of the work done by gravity during each stage of an object in free fall launched from the ground? This is interesting. Work done by gravity. So I launch an object up. Does it have kinetic energy? At that moment. Then you launch it up. Does it have kinetic energy? Yes, it does. All right, so then what, William, as it's going up, is gravity speeding up or slowing it down? So what does that mean about the work of gravity as something is going up? Is it negative, positive, or 0? Yes, because it's slowing it down. Then it stops it, and on the way down, what does it do to the object, gravity? It speeds it up. So what does that mean about the work done by gravity on the way down? It's positive. Does that make sense? Yes. All right. Okay. Make sure you explain that on your answer. On the way up, you're decelerating the thing. On the way down, you're accelerating the thing. Yes, Mike. All right. I'll go there. I'll go there. All right. See? Or if it's absolutely, 100% repeated, you can skip it. You know what I'm saying? Just why repeat this right now. Okay? Yes. I basically put a bunch of questions together to make that, so I made a mistake probably. Alright, so what am I saying? Alright, now we're doing number 5. Okay. In free fall, if you increase the force that throws the object upward by a factor of 4, how many times bigger will the speed be attained in the height it gets to? So, whenever you have a conceptual problem, you have to find the equation that helps you out. This is an example of the work energy theorem at work, right? So, I'm trying to say, I'm going to throw this with a certain force. Are you with me? How does it affect how high it goes? So, what do I have to set up? The work that I do to the high it goes. Height, does it go here or does it go here? Here. So I just think about, at first when I started, how much kinetic energy do I have before I start throwing the object? How much does kinetic energy does the chalk have in the context of the classroom? At the top, how much kinetic energy is it going to have? Right? So is there going to be a change in kinetic really in this problem? No. But is there going to be a change in potential? And they're really asking me about, if I change the work by increasing a bigger force, what's going to happen to the... Are you with me? Practicing that is important. You don't practice that, that's why the practice was due before it started, because you have to practice these concepts. But that's what they want you to look at. A lot of the problems are going to be with this theorem. Alright, so work equals changing potential plus change in kinetic. There is no change in kinetic because it's both the same, 0 to 0. Right? Stop at the beginning, stop at the end. So that means we have this. This is force times distance, and this is mgh. They want to know what happens to the height. So what do? I solve for height. I'm doing how to solve this problem, guys. I'm finding the equation. I'm testing the zeros. I'm solving for what I want to do. So now it's h equals f times d over mg. Now I have an equation that can help me answer the question. They're going to say I'm going to increase the force by a factor of 4. 4 times the force. What happens to the height? What do you mean? Multiply this number by 4? It's algebra. 4 times. You did 4 times this size, 4 times that size. It's algebra. Does that make sense? Did you follow what I just did? I wrote the equation that I needed. I canceled out the 0. I solved for what the problem was asking about. And then I plugged it in my head. If I did it 4 times on f, that's got to be 4 times the height by algebra rules. Does that make sense? Okay, next question. All right. Explain free fall in terms of work energy changes. Oh, we already did this one, so I'll do it really fast. Free fall is this. Okay? So now they want you to explain this in terms of work done to kinetic energy changes. So what is it really happening doing free fall in terms of that? Gravity is doing positive work, which is making the object move faster. But you can also explain the same thing in a different way. Why is the object moving faster instead of gravity doing work? Because it's what? Exactly. That's good. Very good, Jen. That is the only other way to answer it. All right? So There's two ways to think of this problem. Either you think of gravity is doing work, and because of that, kinetic is going up. Are you with me? Or you can think of I'm losing potential, and therefore kinetic is increasing. Does that make sense? All right? I like to think of it in terms of the potential loss because I don't get confused. All right? I don't think of the work done by gravity because I got really confused when I started thinking about that. But anyways, compare potential energy and work done by gravity between someone taking the stairs and someone, an elevator up the tower. Work done by gravity. So let's dissect this problem. Going up the stairs or take the elevator. Either case, you, physically, your weight is being active the whole time. In which case does gravity do more work? Very important question. So I'm taking the stairs up, or I'm taking an elevator up. In which scenario does gravity do more work on you? All right, hold on. So let's see who's next. Lovato, what do you think? Elevator. Why is the elevator Lovato doing more work? Okay, so what is work? What is work? Times the cosine of theta, which is important. You have to think about only the force acting in the direction of motion matters, right? So it means if I'm going from here to here, it's only the force in this direction that matters, because it's the direction of displacement. Are you with me? Now, you see how I displace from here to here? When the force in this direction, gravity doesn't act in that direction, so that doesn't matter, right? So only the work in that direction matters. So this guy started here, and then ended here, right? As far as height is concerned. So work is force times distance. Is the distance difference between the two of them in terms of the distance and direction of motion? No. What about the force? Are you going to weigh differently in both situations? No. So the work has to be the same. That's a very important concept. What is the only thing that matters? Is that it, what is the only thing that matters to figure out the work done by gravity? Really the changing height and the mass of the object. Right? Right. Because it's just the vertical direction that matters. Which is very important. Check this out. This is kind of like a AP physics problem, but I like talking about it. So you have a steep hill. I love this problem. Right? You have a steep hill and a more or less steep hill. And then two skiers, or two balls, whichever way you want to think about it, are rolling down this hill. Right? Now, which one is at higher potential at the start? The same. And if you eliminate friction, only if you eliminate friction, this is important. When it gets to the bottom, which one will have more kinetic then? You would have to have the same. Does that make sense? Because all the change in potential, it becomes kinetic. Are you with me? Which means both balls have to arrive, if there's no friction, there's no mechanical energy loss, and therefore you have to have the same amount of mechanical energy, the same amount of kinetic energy. Does that make sense? Now, if the balls are the same mass, what's the velocity of the balls at the bottom? If they're the same mass. The same. But I thought this ball is accelerating over a shorter distance. All right? Well, yes, it's taking a shorter distance, but it also takes some less. Now let's talk about time. Which one will get to the bottom first? The short one, right? It's because it's covering a shorter distance in a short amount of time. So now which one is, are you with me what I'm trying to say? So this one has to cover a bigger distance, horizontally speaking, right? But there's also less force acting on it, which means the acceleration is smaller. Why less force? Because, it's not, the gravity is not completely pointing down. Some of the force goes against the thing, the normal force, right? So the component of the gravity that's acting in the direction of motion here is going to be smaller on this guy, which means there's going to be less acceleration over a long distance. It's going to take longer. Well, though they will take longer, they will get to the bottom with the same speed because they have the same mass. Does that make sense? Now check this out. mgh, if change in potential, if there is no work, then this is the same, right? So if you write mgh final minus h initial equals mv final minus v initial, as a square note divided by 2. You notice how mass is on both sides of the equation? Right? Do you see that therefore mass does not matter, and that's why objects the same if their masses fall the same way?
Does that make sense? Saying? Now, why aren't they falling at the same rate here, though? Obviously, the same mass fall at the same rate if they're going the same distance. Are you with me? They are not really going the same distance here, are they? They're going the same vertical distance, which means the work done by gravity, the work will be the same. But the acceleration is not the same because the actual distance is not the same. Does that make sense? Now, the moment you throw friction, all bets are off. Because this path is longer, if you have the same friction on both paths, friction is going to have more space to act. Are you with me? So this guy will get there now slower. Does that make sense? If you have friction. So which means if you are on ice, when there's very little friction, but there is friction still though. They got it. If there wasn't friction, you couldn't slow down or turn. Right? But if you're going down an icy hill, right? Assuming there was very little friction, you'll get the speed at the bottom will make no difference. You'll get just as fast at the bottom. But this ride will be longer. Are you with me? So you enjoy your ride a little longer. What I'm trying to say? Than this one would. So a roller coaster that has no friction, that doesn't exist, but a roller coaster that had no friction, right? If it went like this, or if they went straight down, they will both get to the same speed. Are you following what I'm trying to say? You actually could make a roller coaster with no friction. Alright, you can make a MagLab roller coaster. It is my dream to ride one of those. There are MagLab roller coasters. It's so scary. Yes. So you want to do it. Alright, let's move on. Okay, so explain why mass does not matter to how high an object goes when it's thrown or how fast it falls. We already did it. I just did it. Put that down, and that's the answer. Are you with me? Now, basically, if you try to think of how fast it goes up, or how high it goes up, you look at when the velocity that you start decides how high it goes. But if you're trying to think from how fast it goes, it hits the floor, then also you look at it this way. But it's the same way. Are you trying to say if you're throwing it up, you're going to start at a certain speed, that's what's going to decide how high it goes. The kinetic you have at the beginning equals the potential at the end. Or if you think about it, how much potential you had at the beginning will be the kinetic at the end. Whether you look down up or up down, the situation is the same. Mass cancels out. Does that make sense what I'm trying to say? Now look at something interesting. When we did free fall, I'll give you this equation right here. It's called, all right, VO squared over 2G. This is the H max equation. It determines how high you go. Right? Check it out. At the rate of free fall, when you throw it up, how fast are you going up here? 0. So the final velocity is 0. Right? So the final height is a number, but the initial height is 0. Right? You're with me. So what are you left with? You're left with G H final equals M over 2 V initial squared. We're almost there. No, sorry, no answer. Because guess that. Now if I put divided by G on both sides, look what I get. V1 squared over 2G. The same equation. Why? Look at that. It's a true statement from energetics. This came from a kinematics point that comes from an energetics point. That's because energetics is really kinematics and dynamics combined. Look at this. Look at this. The work energy statement, right? Look at that. Force times distance, right? Equals, this is work, right? Equals change in kinetic energy, right? So we can put mv squared, v2 squared minus v1 squared divided by 2. I'm going to rearrange this a little bit, and look what I do. Look by 2fd. What is fd though? What is f? Right, but does that follow to that? ma, isn't it? Alright, so I can put that as MAD equals M 2 mag, right. V2 squared minus V1 squared divided by 2. M's on both sides, I cancel it out. Are you with me? Are you still? Alright, now we're getting somewhere here. Alright, so then, what did I do wrong? Not yet. I knew something was wrong. This 2 is gone. So right on the other side. Right? Okay. Now look what I can do now. I can leave this V2 here and put V2 squared equals V1 squared, because I sent to the side, so now it's plus 2AD. This was one of your equations in kinematics. All right? So you see kinematics is there in the work energy theorem. All right? So the work energy theorem is kinematic. It's a kinematic. So I can go backwards if I want. What is A? A is F over M. Right? Because A equals F over M. Is that a second law? Right? So then I could put 2F over M D. And then if I work backwards, I'll get it up there. So that means the energetics equation, the work energy theorem, is actually derived from the kinematics equations plugging in dynamics inside of them. All right? But the cool thing about it is that it makes it easier to solve problems. For example, trying to figure out the height it goes to, or figure out find out how fast it hits the floor. All right? It's all cool stuff. Continuing. What number are we in? 9. The relationship between now we're doing about springs. What is the formula for a spring? F equals to Ks. So just the force, right? Now, if I put a graph of that, let's make a graph of that, okay? Force and distance. Let's think about this. When I compress the spring, what is the spring going to do? It wants to uncompress it. So the force is always opposite to the direction of motion, right? That's why the real formula has like a negative sign here, right? So if I stretch the spring, the force is negative, just like this, right? Right? Now check it out. Whenever you have a graph, I told you about this, you always think about what the slope means and what the area means. So let's think about what the slope means. Rise over run. Rise is F. Run is, what is the run? X, correct? So what if I do F over X? Look at that. F divided by X, what is that? K. So what is the slope of the slide? The spring constant, right? Now what about the area? Think about the area. How would I get the area of this? 1/2 base times height, right? 1/2 base, what's the base? X. What's the height? F. But what is that? Kx. So let's replace that. 1/2 Kx squared. So what is the area under this curve? Work. Work. So when you have a force times distance graph, what are you graphing in the area? Work. Are you with me? So if you see a force and distance graph, that's what it is. And that's where that formula comes from. The formula is over here. All right? Now that I showed you where the formula comes from, let's think about something conceptual using that. They want you to compress the relationship between compression distance and the work done or the potential stored in the spring. Let's think about it. The relationship between the compression distance and the work done or potential done by a spring. How is this relationship? Is it direct or indirect? In other words, if I increase this, does that increase or does that decrease? So let's think about it. It's easy. Anna? Okay, so I'm increasing this. Is that going to increase or decrease? So is it direct or indirect? Direct relationship. However, is it linear or quadratically direct? If I increase this, does that increase linearly or quadratically? Quadratically, which means if I compress the spring twice as much, how much more energy to get stored in there? Twice as much or 4 times as much? Does that make sense? If I compress it 4 times as much, how much more energy gets compressed in there? 16 times the amount of energy. Does that make sense? So when I get the spring for the balloon and I pulled it 4 times as far, are you with me? I have 16 times the energy. Are you with me what I'm trying to say? So just think about that. All right. So then, answer each of the following and explain your answers. How much work is done by a person pushing against a wall? We already did this. None. Why not? No displacement. How about a car moving forwards at 25 meters per second? How much work is done on the car? How much work is done on a car moving forwards at 25 meters per second? Is it moving at acceleration? Or is it moving at constant speed? If it's moving at constant speed, what does that mean? Is there work? No. So no work because there's no force. There's no acceleration. Now work done on the car. Are you with me? There's the force moving it forward, but there's probably a force what? Slowing it down. Air resistance, drag, something like that. Now, how about a 10-kilogram person going up the stairs at 2 meters per second? Is there work there? It's just going up the stairs at constant rate. Is there work? Why though? No, but it's a going constant velocity though. So why, but it's still work though. Why? Why is there work this time but not on that time? Last time there was no work, but this time there is work. Because what am I doing though? Which means what? I'm gaining what? Which means I'm gaining what? That means there must be work. Are you with me? Alright, here I'm gaining neither kinetic nor potential. So if the kinetic is not going up or potential is not going up, there's no mechanical energy change, there's no work. Right? 11. The angle between a force and the direction of motion is 135. Think about that. What is a 135 angle? Does it pass the 90? So what is the force doing really? Alright? It's a negative force, right? Does that make sense to you guys? It's a force applied like this. Is the work done by this force going to be negative or positive? What do you guys think? Negative, because it's opposed to the direction of motion. Does that make sense? Alright? It's pulling a little up and a little to the side. Right? Yeah. Okay. Now, it might not pull it off the floor though if there's not enough weight. Right? It's going to make the normal force lower though, because you're pulling it up a little bit. So it's going to lower the normal force. Now, what is the sign of work done by kinetic friction? Work done by kinetic friction. Does it have a sign? Kinetic friction. Kinetic friction is always sliding friction, slowing you down. Always. So what does that mean? Negative. What about static friction? Now, earlier today, I asked you this question, and you said, can friction do positive work? And then we said, yes, because it can speed up the car. This is a really interesting thing about that friction. The car is spinning because each second the wheels touching the floor with static friction, right? But that force only lasts a split second. The next second is not there anymore. Another force is there for the next interval where the next piece of tire meets the next piece of road. Are you with me what I'm saying? So it's always a different piece of tire and a different piece of road. That's why it's static. Kinetic would be the same piece of tire against lots of pieces of road. That's sliding. Are you with me what I'm saying? If on the other hand you're getting a new piece of tire with a new piece of road every second, that's static. That can push you forward. However, over what distance is that happening? Is there a distance or is it just a point? Which means how much work is that doing? Exactly. It doesn't do any work. And yet it sends you forward. That's really mind-boggling. All right. So static friction does not do any work. Okay. So I'm correcting something I said earlier. All right. Make sure you pay attention to that. All right. Let's see if I won't necessarily do all of it. Let me just see. Woo! Some of these are math problems, so we're not going to do all of them. Okay, but we're going to try to get at least to where 18 starts. Okay, 13. A 4 kilogram mass is moving with 2 meters per second. A 1 kilogram mass is moving at 4 meters per second. Both objects encounter the same constant braking force and are brought to rest. Which object travels the greatest distance before stopping? Now, these will be in your test, so you got to make sure you can think about it. We got to find what we need to do. They're giving us mass. They're giving us, so this is what you do in physics problems, right? They're giving us mass. They're giving us velocity. They're talking about a force. They're talking about a distance. So we need an equation that has mass, velocity, force, and distance. So it's the work energy theorem, but it's talking about the work done and kinetic energy, because it's going to be like that one. Force times distance equals mass times velocity squared divided by 2. See? Mass, velocity, force, and distance. So you see, by listing what I'm giving, I can figure out the equation. Now they want to know which one is going to travel furthest, so what do I have to solve it for? For d squared, all right? So not for d, sorry, distance. So it's going to be mv squared over 2f, right? Now, the question they ask you is that the first object has a 4 kilogram mass and 2 meters per second. So this is a 4 and that's a 2. Are you with me? So I'm going to write that down. The first one, the 4 is a 2. Are you with me? The second object is a 1 kilogram mass moving at 4. So that's a 1 and a 4. Are you with me? So let's think about what happens. The force that applies on them is the same. So that's not going to change. Right? So whatever number it is the same for both. Let's think about what's happening here. This is a 4 and that's a 1. So that's the second guy has a quarter of the distance, if it was just that. Are you with me? If it was just that, it would take a quarter of the distance because this is 1/4 of that number. So it's like I'm getting the mass and dividing by 4. So that means this will be divided by 4. Does that make sense? But this guy also has twice the speed. Twice the speed squared means what? 4 times. 4 times and a quarter. What does that mean? This is a quarter on the top. But then on the top, it'll be 4 times. 4 times and a quarter, what does that mean? 1. So what's going to be about distance? It's the same. If you didn't follow that, watch it again. Alright, it's being recorded because I don't have time to do it again. But what I'm doing here is that I found the equation that governs it, and I thought about how they compare. The first car is a quarter of the mass. So it should be a quarter of the distance. But it's also going at twice the speed. So it should be 4 times the distance, based on the formula. 4 times the distance, a quarter of the distance, same distance. Alright, that's what I'm doing. Alright, another problem just like that. So if you've been traveling twice as fast, what distance would the car have skidded under the same conditions? Alright, so think about it. The force the same, your mass the same. You're traveling twice as fast. What does that do to the distance? Look at the formula. Twice as fast, the distance. 4 times. Alright, so that's the next question. So 4 times. Alright, another one, the same idea. A block of mass M is pushed against a spring constant K. So it looks like we need a spring constant for this one. Right, so let's do that. So we have 1/2 kx squared, because it's talking about spring constant, so I know we're going to need this one. So you get the mass M and the spring constant K. The spring is compressed of a distance d, and then the block is released. Alright? It is launched by a spring along a horizontal frictionless surface with a final speed of v. So basically they're saying, I'm going to use this potential energy here to make the thing move. So that's basically relating the potential energy to the kinetic energy afterwards. Right? Because changing potential equals changing kinetic. Alright, so then, he's saying this time, the second block has a mass of 4m. Guys, you gotta practice these kinds of problems. Like seriously. The book has a lot of them. So you're smart. If you don't do it in class, then you do it at home. You've got to get better at identifying what formula. You know, see how I do it, what formula that I use? Because I knew he was talking about the spring and something moving. So it's potential and kinetic. I have to relate them to each other. Because whatever potential I have on the spring is going to become the motion that it gets. Does that make sense? Alright. So they're saying now, I'm going to increase the mass to 4. Are you with me? Well, I'm going to increase the mass to 4. Are you with me? And the velocity is increasing to 2v. So I'm putting this 4 times, right? And I'm putting this 2 times. Does that make sense? Okay. They're asking you how much more do I have to compress to make that happen? So I have to solve for x, for x, because that's what they're asking about. So before I do it, I'm going to solve for x. How do I solve this for x? 1 happens on both sides. So what can we do it? Yes, cross it out. I got to divide both sides by, and then take the square root. Are you with me? So it's going to be x equals mv squared over k, square root of that. Are you with me? Alright, so if that's true, if I make this number, what did they say they're going to do it? 4 times, and this number 2 times, but 2 times squared is also 4 times. So 4 times 4 makes it in the square root, so it means 4 times the distance. Do you see how you do that? You're going to find the equation, solve for what they're asking for, plug in the numbers, and see what happens. That is the same process every time. Alright, let's do another one. Okay. Oh, we already did this one. Draw an fx graph for the force exerted by a spring and explain the meaning of the slope and the area under the curve. I did that one already, right? Okay, so now you do it yourself. How would the amount of power change if you did the same? Oh, power now. What is power? Looks like we need some time next class to finish it. What is power? Does anybody know what power is? Work divided by time. Okay, so now look at their... Oh, by the way, what is work? What is the formula for work? Force times divided by time. What is distance divided by time? Velocity. So what is another way of thinking about power? Force times. Now, think about that. Why is it better to have more horsepower? With more horsepower, you can drag something heavier up a hill, or you can make your car move faster. Does that make sense? Dragging the same load. Are you with me? So either I can drag something heavier, or make it move faster. So when you have, for example, a car, why is it at a certain point, no matter how much you're accelerating, you can't go faster? Because the wind power, drag starts slowing you down. Are you with me? But if you have more horsepower, you can oppose that force and go faster. Are you with me? So that's why horsepower matters. You can get more force and more velocity. That's why horsepower matters. Now, with that in mind, you're asking a simple question, right? How would the amount of power change if I did the same work in half the time? Same work in half the time. How would I do the power if I make this half? Doubles. Very good. Follow-up question. What if I use 6 times the force? 6 times the force, what happens to power? 6 times the power. What about 6 times the distance in half the time? 6 times the distance in half the time. So it's a 6 over here and a half over here. What does that do? 6 times 2 should be 12. Because it's half the distance. 12 times the power. All right, we'll pick it up from number. Actually, the rest is all mathematical. So next class is practice day. All right? Make sure you guys do that. I will go back on what I said. It is okay. You can always do conceptual and mathematical questions. Just like you can always do labs. However, I strongly recommend you not to always just sit there and do math and things. All right? Break from the mold. Do something active sometimes. All right? But you can always do conceptual and math problems, and you can always do labs. The rest, you can only repeat once every 3 topics. I'll see you guys next class, which is Monday. Until then. Oh, we see Friday? God damn it. All right, I'll see you guys Friday then. See you guys then.